All right, so I guess I'm going to start with my motivation for the talk. So one of the things that always kind of confused me about Python is you write something in Python, and then you click run, and then the computer does some magic, and it pops out an answer for you. And when I was looking through the CPython interpreter, the core system that actually runs Python, the thing that conceptually gave me the hardest challenge of understanding was the runtime environment. So I'm going to start with a brief overview of what the CPython interpreter is and what it does. So let's say I'm a clever, lazy programmer who was given the assignment that they need a program that is completely secure and bug-free. So I was like, if I just delete everything, then it's perfectly bug-free and secure. So how CPython works is that there's basically two parts. There's the compiler that converts any Python code into a bytecode, and then there's the runtime, which is the thing that actually runs the bytecode itself, and that actually executes the Python code. So just going over a quick overview, the compiler, you have a reader that reads the arguments, reads how you run Python, the lexical analyzer that basically splits it into parts. So kind of like I already did with, I already pre-processed the args for the bash commands. It also does the same for Python. The parser that turns it into tokens, the intermediate code generator that turns it into an AST, an abstract syntax tree, an assembler that turns it into a bytecode. All of these things are very complicated and deep, and we'll be here all night if I got into any details. So just know that the code on top just gets turned into bytecode. And then, so once we got the bytecode, the runtime basically does two main things. One, it keeps a frame stacks of frames of Python code, which I'll tell you about what frames are later. And then it has the memory allocator, which is its own complex subject, which we could spend all night on. But I'm just going to focus on kind of like how the runtime actually executes your code and how it runs it. So first, let's discuss what a frame object is. It's not important. It will be important later, but I think it's also good to know. So basically, every time a frame object is any Python code that's in a function, it's compiled into bytecode, and it has a set of instructions. The CPython interpreter then wraps that bytecode into a frame object that includes both the code, which includes stuff like location, args, and various constants. If you ever want to know why recently Python now underlies in your traceback, like which line or which area stuff is, it's because of the code object. And around that code object, we have stuff like builtins. That's how the runtime connects with the built-in objects, global variables, local variables, linkages that helps the runtime link to different parts of the code, and mostly the previous frame, and then the evaluation stack, which is probably the majority of what I'm going to focus on in this talk. So the evaluation stack is basically modeled as a stack machine. So at the core of the Python interpreter, you have basically what we call a stack machine for executing the code. Basically, Python feeds the frame into pyeval frames x in python.ceval, and then you might send it the whole frame, but it just focuses on the bytecode. And just for a little bit of comparison, stack-based machines include CPython, JVM, and WebAssembly, while register-based machines are LLVM compiled C code or C++ code, the GCC, and the V8 engine for JavaScript. So you might be wondering, what are stack-based, what are register-based virtual machines or interpreter architectures. Ooh, sorry. So the core of the VM architecture, so at the bottom left, I forgot the label, is kind of like the core of what, so one thing about interpreter architecture, virtual machine architecture, is that unlike code, you only have a limited number of memory spaces based on the physical hardware. So basically, what we have at the bottom left is an example of maybe a simple stack-based operation where we push the constant 2 onto the stack, and that just pushes 2 on the stack. And to the right, we have an example of a register-based architecture where we have 4 registers, 0 to 3, and we have an operation called move Q. If anyone's familiar with x86 assembly, we move the value in, well, actually, if it was x86 assembly, you would add parentheses, but I'm simplifying it. You move R1 to R3, and as we see, it basically just copies the value. So basically, the core differences between stack and register is that stack-based machines, you're only allowed to access basically the top couple of memory, or basically values at the very top of the stack, while in register-based architecture, you're able to interact with any value within the register. So you could do R0, 1, 2, 3, or 1, 0, 2, or 3, any combination. And the main differences between the two architectures are that stack machines are a lot easier for compiler developers to develop for and make, while register machines, while more complicated, are a lot more efficient. And the CPython interpreter uses mostly a stack-based machine for its interpreter. And this kind of stuff is very abstract, very hard to understand, so I think I'm going to start with an example of a simple example for Python and how its CPython stack machine actually goes through the code and executes it. So we have a very simple function. We have a times parentheses b minus c. I give it the examples a equals 2, b equals 4, and c equals 3. And as you can see before, here's a picture of the code. It's very simple. And to the right is, so if you remember what I talked about, kind of like the compiler part of the CPython interpreter, it basically takes what's in the picture and then disassembles it into bytecode. Into bytecode, we disassemble it, which means the bytecode is just a bunch of 0 and 1 values. But then we disassemble it, so basically we turn it into things that you can easily read. And to point out, you have 30, which refers to just x equals a times b minus c. And we have these operations. And 31, so let's go through and see how this disassembled bytecode is worked with the Python interpreter and actually does the logic. So let's start off with the first part of the bytecode. So we have 30 here, which stands for the line number. 2 is the character offset. The third number is the operation code. The fourth number is the parameter. And then here is the fifth number is basically the disassembler gives us this. This doesn't actually exist in the bytecode, but the disassembler prints it out for us to help us better understand. Like, for example, binary ops are just any kind of binary ops that the machine can do directly. And to do minus, we give it binary ops parameter 10. If we want to do we have to do binary ops times 5. We have to pass in 5 so that I can do a binary op of times. And it helps us understand the code because we don't really understand what does 10 mean, what does 5 mean. So basically, we're going to start with the first instruction. We have an empty stack, and then the instruction is load fast, and we have load fast parameter 0. This is actually a design of the Python interpreter. Load fast is 0. We all basically within the interpreter knows if we want 0, it means load the argument of 0, because one of the things about anytime when you deal with a runtime or low-level CPython code is they try to do it as efficient as possible. So they do like basic numbers like 0, 1, and 2 for the arguments. So we end up with the state of 2 onto the stack. And then we go on to the next state. We load fast. And if you're wondering how this code is done in the right order, so it does it correctly, that's the job of the compiler, and that's a whole complicated deep end. And then we basically load 4 onto the stack, followed by 3. So this is the stack before the load fast operation of loading the value in C, and this is afterwards. And as you can see, it adds 3 onto the stack, and now we're kind of in our first interesting operation, binary ops. So what binary ops does is that it's a special type of, there are many different types of operations for the CPython interpreter. I just took a simple example, but there are hundreds. But one of the things binary ops does is that it pops the top 2 values from the stack, and then based on kind of like the parameter you gave it, so we gave it 10, which means we want to do a subtraction binary ops. We kind of do the operation here, and then binary ops then pushes the new value onto the top of the stack. And then we do the same thing. This is a little typo, but we're in binary ops 5. We pop out the top 2 values, implement the binary operation, multiplication, and then we push it back on the stack. And then store fast basically just means that we save it as a local variable. And then we go on to line number 31, where it's load fast, which means basically we're loading it into another local variable or special registry value, and then we return it. And so this is very abstract, kind of very abstract, very low level, but I think I can show good examples of where this can be used and how it can be useful. So I'm going to start with a function that does factorials and recursive, just as an example. Yeah. So let's remove the terminal first. So basically, with the inspect package, you can get what is the current stack, current frames of the code you're running at that moment. I have a function here that basically formats it, because if I didn't format it, it prints out all the information and it's almost impossible to read. So where did my terminal go? So if I do, we have, as you can see, kind of like how the function kind of runs. I print out the stack. So basically, if you think about how factorials work, I have a recursive code here, and you can kind of see, it first checks, I start with 5, it's not less than 2. It then pushes 5 down and adds 4. It's not less than 2, it's 4. It just keeps on going until it's down to 1. And then once it's at 1 and return, the functions are able to solve each other. And while this is might be an easy example, I found a large use of stacks, kind of like this kind of working with, well, actually, I'm going to show you there's actually a better way of doing this. So I'm using expect right now, but one of the big reasons why frame had so much, if you think about it, like why are we, this is the very low level of Python. Every time we do a tiny operation, move a value, add a value, load a value, we carry the baggage of all these other stuff about the code. And the primary reason why Python does this is for PDB. So if we just replace this with breakpoint, and then save it, and then run again. Now we're in kind of like the command line value of PDB. C just means continue. If I type in where, it actually gives me the kind of like the traceback you would normally get for each level of the stack. So right now I'm on level 4, if you remember the printout before. If I press continue, continue again, we're a little bit deeper in the stack. And as I then continue again, we're 5 levels down. We're actually, and then I can print out the args is when n equals 1. And when I'm in the debug, if I press U, or up, I'm actually at n equals 3. So by doing this, by having knowledge of the stack, so basically as I showed you before in an example, that was like simple binary commands. But Python also treats whole frame objects the exact same way. So if you have a recursive function or functions that call each other, you can go up and down the stack and see the value, which I found very useful if you're ever running something like gRPC requests, and the thing that was causing you the error was very low level in the code of requests, but the thing that caused the error was you calling it several levels on top of the stack. And yeah, that's kind of like, and then finally, my references. This has been one of my primary references for learning about CPython. It's, there's 2 things. There's the free online guide on realpython.com, and then there's the CPython internals book, which is available for sale right now, and kind of gets really into the details of CPython. Much lower level than I did currently. And yeah, so any questions? I'm just going to leave it up.
Yeah. Can you go back to the code for me? Just see where you put the break.
So, yeah. The file is named Fibonacci because my first idea was to do Fibonacci, but it was kind of a complicated example, but I guess I could easily do Fibonacci. Well, just have to rename it. Hmm? I'm just curious myself. So let's see how it does. And then, I could actually show you what stack would look like without my helper function too. Yeah. But yeah, no. So yeah, like breakpoint is actually built in since 3.8, I believe, and it seven or 8. I think it's 7. You're correct. But it basically, whenever you're running code with PDB, it basically forces it to stop at that point.
Another question.
Mhm.
So you mentioned why it's simpler using the stack, but why it's not with assembly?
So I think,
Can you repeat the question?
so I'll repeat it. So basically, he's asking why is it simpler for compiler developers to use a stack-based architecture than a registry-based? And the big thing is stack-based, you only have access to the very top of the stack. So versus, well, registry-based, you have access to all of the stack. Well, not, you have registry to all the registries, which I think for x86 64 architecture, I think there's like 16 registries, and some of those registries are special, like there's one registry for the top of the stack pointer, there's another registry for return value, there's special registries for arguments, and so if you think about it, if you're designing, let's say, operators as a compiler developer, you only operate it on the top value, but if you do a registry base, you have to think, you can technically, if it takes in 2 arguments, you're doing against 2 registries, you can basically do it against every other one. So it's basically constant consideration for stack-based, while it's almost n squared for registry-based.
Is it because I have to know the address for each?
It's just with registry-based architecture, you can basically use the value in the memory address for every single registry, versus in a stack-based architecture, you can only use the very top of the stack.
I'm just curious, doesn't Python interpreter have multiple stacks?
It does. That's actually, so each frame object has its own evaluation stack. And how stacks and that's a lot more complicated because there's something called thread state, which also kind of can control the behavior. So whenever you leave a frame object, I think there's actually a C macro that does a whole bunch of crazy stuff to determine where to jump to and like where to optimize. I don't want to keep you guys here all night for that, so I was gonna keep it simple. Mm-hmm.
I was curious, go back to slide 2, how would it compare to ChiPy or ChiPy?
So I'm not very familiar with the architectures of PyPy or other interpreters, but I mean, what I'm showing you kind of like with the compiler and runtime is kind of standard computer science interpreter and even compiled code. So with the compiler, these 5 steps, I actually took in from the Dragon compiler book. And then for the runtime, in interpreted languages, you have basically a program that gives you an extract runtime where the C, the LLVM, GCC compilers actually generate the runtime with assembly machine code instructions, and I definitely tried to avoid that in the talk.
Gets hairy.
Mm-hmm. Yep.
Okay, in Python, the dunder functions implement binary operations, at least at the code level. When you get down to here, does binary op 10 do a floating or an integer multiply, or is it a general multiply that then the C runtime?
So it's actually in a file called a ceval, Python ceval.c. You have to look at the C code. I was just kind of, so basically there's a gigantic switch statement for the, so when I kind of show kind of like if you look at the binary code right here, disassembled binary code, this load fast is actually a value, like a number value, integer value, which is fed into a pyeval_eval frame x that, or a similar function like that. I'm not sure if that's the direct one. And then that's actually just a gigantic switch statement. And I would have to look up the code for binary ops, but because they call it binary ops, I assume that they basically just have, if it's small enough, they basically have the compiler do the machine instruction of the binary op. Mm-hmm.
Is there a load slow?
Actually, I don't know. You can find them, all of the operations in the dis documentations in Python.
I think there's a load faster.
Really?
I think one of the optimizations of like V11 and V12 statically does
Like
you have to know the value.
there's a reason why I chose a simple example, because I don't want to give a crash course. And in a way, if you understand assembly programming, kind of this stuff makes a lot more sense, because there's a lot of stuff that maps onto assembly programming, like one thing we're used to as programmers in the normal languages is passing parameters to like an if statement. But in this low-level virtual machine programming, like for example, if we have a register-based machines, there would be actually registers that are flags. And then so we would do a compare operation, and then it'll change those flags. And then we have another compare to do like jump to another section of code. So it takes two operations to do an if statement, while in normal code, it would just be in one segment. And I think similar thing with so for example, like I think with the comparisons with a stack machine, you would have to basically you would have to do two statements. You have to load the constant you're comparing, do the compare operation, which might add a value on top of the stack, and then I'm not sure about this, but I need to look at the documentation. But it's assembly program it makes a little bit more sense if you learn a little bit of assembly program, especially looking at this level, but it's not very useful if you're doing web development.
Let's have a round of applause for Alexander.
Why am I clapping myself?